So you know about parametric time automata, about synthesis of timing parameters, and you know also about interval Markov chains with parameters. And now we will talk about Petri nets. So in Petri nets we have places, transitions, and tokens in places. And we say that the transition is enabled if it has token in its input places, for this transition, for example. And when the transition is enabled, we will fire it, and we can fire it by taking the tokens in the input place, and putting them in the output places. And we take as many tokens are specified on the input arc. So here we do not have a value, so we say that it's 1. And we put as many tokens as specified on the output arcs. So here we have 3 tokens put in this place and 1 token put in this place. Then we can fire T2, and because we had tokens in this place and this place, and we will take 2 tokens from this place, 1 from this one, and put 1 here. So now when we want to parameterize such a model, we have several possibilities. We can, for instance, put parameters on the initial marking. So here we say that we have A tokens in this place. We can put parameters on the input arcs or the output arcs. So here we say that we will need A token to enable this transition, and we will put B tokens when we fire the transition. And here also we will take A tokens. So initial markings, for example, could model a number of processes, an initial value for a semaphore or whatever. For input arcs, we will specify some numbers of items to take or some number of processes to synchronize. And for output arcs, in the same way, we will have processes that are spawned or number of items to give and so on. So now the basic problem that we consider is coverability. So what is coverability? It is that we want to reach some marking which is greater or equal to our actual goal marking. So it's a bit weaker than reachability. We don't know exactly which marking we will reach, but we know that we will reach a marking which is greater. And this is important because with coverability, we can actually know if a transition can fire, because we have enough marking to make it enabled and then fireable. So this includes in particular many safety properties which can be modeled by the firing of a transition to some error marking. So coverability is known to be X-space complete in Petri nets, and we will now extend this problem to parameters. So first, a small example of coverability on our former example of Petri nets. So here we have some marking that can be covered, for example, the marking with 0 on each component, because obviously every marking covers this one. Then when we fire this transition, we can see that we have a new covered marking, several new covered markings. So for example, here we have 1 token, at least 1 token here, 1 token here, and at least 1 token here. And here it doesn't matter, so we can have 0. And then by firing this transition, we can reach a whole new family of markings that are covered by this net, namely those that are greater than this marking. A contrario, there are many markings that cannot be covered in this net. For instance, we cannot have at the same time 1 token here and 1 token here. So this is this marking. And we cannot have at the same time 2 tokens here and 1 token here. Or we cannot have more than 7 tokens here. 7 tokens here. So now what does it mean for coverability in the parametric setting? So we can define 2 decision problems. So the first one would be existential coverability. Does there exist at least one parameter evaluation such that some marking is coverable in the instantiated net? Or universal coverability, is some marking coverable for all the values, the possible values of the parameters? then of course the most interesting problem will be synthesis, as we have seen in another sequence, in which we compute all the values such that some marking is coverable. So let's stay on the decision problems for now, and we will consider first the most general version of parametric Petri nets, where everything can be parameterized, going from initial markings to arcs. So in this case, unfortunately, we have an undecidability result, so we can simulate two counter machines. So two counter machines are simply a finite automaton with two counters, integers, non-negative, and we have instructions which permit to go from one state to another, which can either increase the value of one of the counter, or test if it is 0, or decrement the value of a counter. Since the counters are non-negative, we will expect that we have a test before every decrement to be sure that we do not reach a negative value. So we have a small example here of a machine. So we have not specified here the initial state, but we could, for instance, suppose that it's P1, and we could also define an halting location, an halting state, which we have not done here, but that could be done, and it would be useful for the decidability problems afterwards. But let's stay on this simple example of machines. So we say we have only two states here, and we start in P1 with both counters being equal to 0. Then we can execute this instruction and increment the value of C1 by 1, and then we can, since we are in P2, we can execute this instruction, increase the value of the counter by 1, and then we are back in P1, and then we can increase the value of the first counter by 1, and so on. So here we can see that this machine will never stop because we do not reach a halt location, and also the value of the counters is unbounded. So we know from the results of Minsky in the late 60s that the halting problem for two counter machines, so deciding whether we can reach some halt states in the machine, or also the boundedness of the counters in such machines, are both undecidable problems. So to prove that coverability, existential or universal, is also undecidable for parametric Petri nets, we will reduce these two problems, halting and boundedness of the counters, from two counter machines and model them using parametric Petri nets. So here is how the reduction works. So we want to have widgets for incrementation of the counter. So this would be this widget, for decrementation of a counter, and for the 0 test of a counter. As usual with Petri nets, it's this part which is the most complex and the most interesting. But let us focus first on the increment, because we have several things to see here. So we will split, somehow duplicate the place for the counter here with a dual place here, such that at every moment in the execution of the machine, we will have the sum of the number of tokens here and the number of tokens here, which is equal to some parameter in the system, which is A. So initially we see that this transition will initialize everything in the machine, and it will put a token in the dual place here. So when we have a token here, it models that the value of the counter, C1, is equal to 0, and then this corresponds exactly to the number of tokens here. So when we want to increment, say we were in this state of the machine, modeled by this place, and we want to increment the counter, so we will fire this transition, take a token here, and put it here. So the value of the counter modeled by the number of tokens here has increased, and the dual place here, its value has decreased. And now we see that perhaps when we do an increment like this, we do not have any tokens left here before this transition is not fireable. So in this case, it means that we have all A tokens in this place, and we can, instead of firing this transition, which is not possible since we do not have a token here, we can fire this error transition and go here. So decrement works exactly like in the same way, so except that we take tokens from here and put them back in the dual place. And then for zero test, as expected, we will test that we have exactly A tokens in the dual place, which means that there are no tokens in the C1 place. So when we want to test for alting of the machine, we can just test if we reach some place like this one, which corresponds to the alting state of the machine. And if we want to test boundedness of the machine, of the counter of the machine, we will just use this error place. So how does it work? I think it was a slide before. We will see that if the counters are unbounded, then for every value of the parameter, there will be a moment when the value of the counter, the value of the parameter will not be big enough to allow for an increment. And so we will go invariably for every parameter valuation to the error state. And when so this would be for universality, and for existentiality of the parametric of the solution set of the parameters, we will need just a valuation of the parameters which is big enough to allow the run of the machine, since we know that it is finite, so it has a finite number of increments, and if we take a value big enough, then we know that we will be able to simulate correctly the run of the machine. So this means that for parametric Petri nets, the most general class here, we have undecidability, and then we can, as usual, when we have undecidability results, split our most general formalism into subclasses and hope to get some decidability. So here maybe we can first try to split between parametric Petri nets only with initial markings that are parameters, so place parametric Petri nets, and transition parametric Petri nets in which we put parameters only on the arcs of the model, so input arcs, output arcs. So as we have seen just before, this model is actually undecidability is actually undecidable too, because the previous construction of the simulation of the counter machine uses only parameters on arcs. So we can further distinguish in this class, and we will distinguish on whether we use parameters on output arcs, that would be here, or on input arcs only, that would be here. And then if we put both of them together, we get distinctive PPN, which means that we use parameters on both input arcs and output arcs, but the difference with this one is that we cannot use the same parameter both on an input arc and on an output arc. Then below we have normal Petri nets, which are just parametric Petri nets without any parameter. So there are a few relations that were not shown in the previous picture. So we will now see how there is a relation between initial parameterized marking and output parameters. So we can very easily go from initial markings that are parameterized to only nets with output arcs that are parameterized. How do we do that? We just add an additional transition, which is the only one that is enabled at the very start of the net, with an additional place here. And this transition will put all the tokens which correspond to the initial marking in the rest of the places. So here we had a marking which was 1, A, B, and here we have output arcs which correspond 1, A, B, and we can thus very easily simulate Petri net with a parametric initial marking. In the other direction, it's a bit more complex. So we have a parametric Petri net with an output parameter, and we want to model it with an initial marking that is parameterized. So how does it work? We have this widget here with 8 tokens in this place, and the idea is that when we fire the transition, we can enable this widget, and then if everything goes normally, I would say, then you will be able to fire this transition 8 times. So put all 8 tokens here and a copy here. And then if everything goes nominally, then you would fire this transition again 8 times. And put back the 8 tokens here. And we are ready for another firing of the transition. And we have indeed put 8 tokens in this place. Of course, it's always possible in the first step or in the second step that we do not fire this transition or this transition exactly 8 times. In this case, then we would have some leftover tokens here, and in the end, we would not have 8 tokens here, but less of them, and also here. But it's not a problem because this net will be able to do less things than this net. Because we have less tokens, so in terms of transition sequences in the net, then we have less behaviors. So basically, the nominal behavior will simulate all the others. So for coverability, it's not a problem. So we can complete a bit our picture. So we have a relation here, 2 different types of relations. Between initial parameterized marking and initial and parametric output arcs here, and so now we can see if which are decidable. The most obvious one to begin with decidability would be initial parametric markings, because we can actually simulate them with normal Petri nets. So how do we do that? We will just say that this Petri net with an initial marking of 8 tokens can be simulated by this Petri net with an initial token injector here that will put as many tokens as we want, and then when we have reached the number of tokens that we are interested in, we can just fire this transition, which will disable our injector, and then it will enable all the other transitions of the net. And in this case, you see that we will have some marking which is coverable if and only if there is first a possibility, a run that will put as many tokens as necessary in the initial places, in the places that were initially marked with a parameter, and then which proceeds to the marking to be covered. So like this, we can simulate and detect the existence of a parameter evaluation that permits the coverability of a marking. So this is for existentiality, and for universality, of course, it's easy to see that putting all parameters to 0 is the worst case. Since we are interested in knowing whether it is possible to cover our marking for every parameter evaluations, we can start with 0. If this is possible, then for sure it will work with all the other markings, and if it's not possible, then we can stop because we know that it's not universal. So we can complete a bit our picture. So we have decidability here, and as I said before, thanks to our reductions, we have equivalence for coverability, so we can also say that it's decidable for post-T PPNs. So now to complete our picture, we will focus on parameters as input arcs. So this is a bit more complex, not for existentiality, because dually to the previous case, we have that 0 is the best case, because it means that we take no token from here to fire this transition. So since we leave the most tokens in the net, then this will correspond to the most permissive behavior, the most the biggest behavior. So if it works for 0, then it's good, and we know that there exists a parameter evaluation. So if there exists a parameter evaluation, for sure 0 works. And for universal coverability, then it's much more complex, and I will not go into the details. But the main intuition is that to fire a transition like this with an initial with a parameter here, then since it's universal, then you would have to be able to put as many tokens as you want in this place. So basically, that the place is unbounded. So we can use this fact together with the notion of simultaneous unboundedness from Demery to create a widget in which we will have several copies of the net, and they will record the order in which we enable parametric transitions by verifying that the preconditions of these transitions are always unbounded and in sequence. So doing that, we have a construction which is a bit complex, but which reduces the universality of parameter evaluations for coverability to the, even for simultaneous unboundedness of Petri nets, of parametric Petri nets, to the simultaneous unboundedness of regular Petri nets. So finally, we have this, and since we have both of them, we can easily combine both techniques, and we get that actually it's decidable also for distinct PPNs. So it remains the problem of synthesis. So synthesis is the most complex problem. It's not a decision problem, but it's a computational problem. So we want to compute all the values that permit coverability. And it's not feasible in general because, of course, since the existential problem is undecidable, we cannot do the synthesis problem, which is more general. But we can restrict ourselves to some subclasses, for example, post-T PPNs. In this case, it's easy to show that the solution set, the parameter evaluation set, such that some marking is coverable, is upward closed. It means that all the markings that are greater or equal, component by component, are in the set. And then we can use a well-known algorithm by Falken and Janssen, which permits to compute a finite basis of such sets. So we can do it for post-T PPNs. So for pre-T PPNs, it will work in the same way, except that we will compute the complement, actually, of the solution set, because the solution set is downward closed, so its complement is upward closed, and we can use also this algorithm by Falken and Janssen. Then if we want to get back to our more expressive class of distinct T PPNs, we have practical issues, because we cannot represent the solution set with a formalism for which emptiness of the intersection with equality constraints would be decidable. Why? Because otherwise we can decide the existence of a parameter evaluation for coverability in general parameter Petri nets. How does it work? You just take a general Petri net, and then of course it has parameters that are both used as input in input arcs and in output arcs. Then you will split this parameter in two parameters, one used only in input arcs and one used only in output arcs. Then if we suppose we can compute the solution set, then we do it. Then we intersect with the constraints which correspond to both versions of the same parameter are actually equal to get back the real values of my original net. And then we can just test emptiness in the set that we have obtained, and then we can decide if the solution set of the original Petri net here is empty or not. So obviously, since this is not decidable, then those steps here, intersection, emptiness of the intersection with the inequality constraint is not possible. So as a conclusion, we have here a class of parametric Petri nets which is expressive and quite interesting in terms of modeling power, but of course it's undecidable in general. But still we can define meaningful subclasses for which it's decidable. And for these subclasses, we can prove that parametric coverability, be it existential or universal, is actually space complete. So then the main remaining work would be to find efficient synthesis algorithms. So both in the simplest cases, for which the algorithm of Valk and Jensen may be not very efficient in practice, but also for the general case, we would like to maybe to have approximate algorithms to get a part of the solution in an efficient way. So now let's see how timing parameters can be introduced in Petri nets. So of course in time Petri nets, much like they were in time automata.